the problem. Okay, here is I usually focus on the clinical environment, not just imaging. Clinical environment, I emphasize clinical environment. Okay, U is the image to be reconstructed. B is the data. There's a lot of uncertainties there. A is some physics. A could be depending on nonlinear, could be nonlinear. But I would like to emphasize Greenness said that is one of biomedical engineers in Norway. He said without modeling, it is not a science, but you should not be a slave of the model. I try to emphasize this part. And this means that you must understand the uncertainties in modeling and practical limitation associated with the measurement sensitivity, specificity, and noise and data acquisition time and so on. Then if you should understand that, then you can apply the clinical environment. And this one is maybe it's just me. It's like it's just naked king. It's something self-malignant law. And also this is could be me is just narrow scope. Okay, let us start with the very simple thing, easiest thing. So maybe this could be a force inverse problem, X-ray CT. X-ray CT is let's look at the A is the radon transform. U is the tomographic image of this one. So this problem is that you X-ray is projected this way. This is projected data. That is B here. This one is put in here, and then you rotate in the 360 degree all of that region. Then you can get the sinogram data. The inverse problem is that using the sinogram data, you try to reconstruct the cross-sectional images. That's the typical well-known CT problem. But this model is not correct. This model is correct in the human body, usually in the soft body, but it's a bone and metal is different. So there is a mismatch. The AU is not equal to B, actually. That's different. So you need to understand the uncertainty of this thing. Because of that one, all algorithms is assumption that data is the radon transform that one. But that is not true. In the pen and human body contains the metal. So here is this is the result. The human body contains is a metal, then you have this. In United States, more than 20% of patient CT scan contains a metal. On the head, almost more than 90% person has a metal. So issue is that, okay, this is a typical Nobel Prize winner is that the filtered back protection algorithm is how can you reduce the metal artifact? Look at this one. This image, using this one, you reconstruct this image. But this one is not, because of the metal is here. So that's why metal streaking artifact make this type of artifact, all of this type of artifact. Here is the joint is here. That's the reason why this metal artifact. So here there exists the serious difficulty in analyzing the X-ray data, which depends non-linearly on the distribution of the metallic object. So this is the recent challenging issue. In the 20 years ago, very few people has a metal. So metal is not serious problem. Right now, it's everybody's metal. Okay. So maybe many people think about the total variation. But warning to scientists is that provided a clinically useful image rather than visually pleasing images. That's the important. The last 3 decades, various metal artifact reduction method has been suggested. However, existing MAR method, MAR is the metal artifact reduction, does not reduce the metal artifact effectively. They may introduce the new artifact which do not exist before the application of the method. So maybe some people think about the impeding method. There is some missing data here. You may use the impeding data. But my opinion is the current impeding data does not work. So that is the impeding-based. If people use because of the metals there is some missing data around here, they use just impeding that part. But that's a limited performance. Inaccurate interpolation of the projection data can introduce additional streaking artifacts to the reconstructed image.
No surgeon will make a surgery with the inpainting based on an image with inpainting.
But the sinogram data is there's something. Okay, I explained clearly more in painting. Okay, I did experiment. Okay, here's a tooth. This is a metal. This is something like I cut it with a knife and put it here, and then I take the X-ray. This is the exact X-ray image, but this part is hidden. Some teeth shape of teeth is hidden. So you use the total variation. Okay, this is the result of the total variation. Okay. This is far from the case here. This is a limitation of the total variation. So if you use the total variation and try to reconstruct CT image, somehow they make the additional artifact. That's the limitation of that part. So you need to develop the other method. This is my student proposed method. Here nothing is showing, but if we take the Laplacian, then you can see something around there. And then solve the unity PD, then you can get this type of image. Okay?
Do you have the ground truth?
Yeah, you take the Laplacian in here, but nothing is, but there's a little data. This one does not see it, but if we take the Laplacian, then you can see this part. Okay? And then do it again, solve the Poisson equation, you can get it. But this is a case, this is a homogeneous cases, yeah? Because taking a Laplacian, that part is really difficult. But generally, it is very difficult to handle.
One question is, I mean, you have basically inpainting in the radon in the sinogram domain, and when you then, because that's where you eliminate the streaking artifacts, right?
Yeah.
And when you then impose that you don't inpaint the sinogram, but inpaint the radon transform of an image, and you get a sinogram that is in the range of the operator, that will actually not look like having like a constant region just inpainted. It will actually look more like a sinogram. So it's not really the real comparison here, or I mean, it's.
I'll explain that again later on. Okay, that's also that's not also working on. Okay, I'll answer the question later on.
Yeah.
So okay, that's the reason why I suggest selectively instead of the regularization, just take off the artifact. That's my goal. I asked to my student to do it that one, and my clever student, much clever than me, he is my teacher. The concept developed he found artifact is completely determined by geometry of the metal. And we discussed it to medical doctor. Geometry of metal is I know, I'm doctor, I know the implant, shape of the implant. So if you know the shape of the implant, can you remove the metal artifact? Then, okay, then I can do it. So he developed the method using these geometry of this domain. So using the geometry, it could remove the metal artifact. This is some first version. And then that paper is the 2017 CPAF or 2016. Now I answer your question. Okay. Drawback of the using the this is every day we talk about this one. Drawback is like this. Okay, here, okay, you can easily. Here, artifact is a very local region. Okay, artifact. If you repair this one, then you could get the good image. Here is some markings, and you try to see this one because this is too metal. But artifact is only this place. But problem is this. Okay, in order to solve AX is equal to B, okay, major problem is that you take the transpose both sides. This is a major problem in the method. That one is my student found it because originally this one contains error only this small region. But once you project the range space, this data is put in the range space, then artifact is spread all over the place. So reconstruction, whatever you do, whatever sophisticated reconstruction, you use this data, and then there is a problem. So the question is how can you handle the problem? That's so this is a local noise, somehow local. This makes the global noise. That's the problem. So this one is recently you found it. So that's the reason for 30 years research of the modern method, they're not successful. Whenever you use whenever you try to solve this problem, if you take a transpose, then you have a trouble. So before taking a transpose, you have to repair it. That's the key word of but this is a challenging issue. You just found this year. Okay. Now let's change the other topic. I tried to say many topics about it. This is MRI. MRI is E1. It worked in E1. That is also it's appeared in the science. Deconvolution problem. Okay, here. This one is a very chi is a susceptibility. Susceptibility is ion content. Ion content is somehow related to Alzheimer's, Parkinson's disease, something like that one. Because its ion content is here, if you apply the MRI is magnetic field. Because due to the ion content, that is the magnetic field is a little bit distorted. Using that data, they try to understand, they try to diagnose the Parkinson's disease or something like that. Okay, the physics is complicated. I cut off all physics, just mathematics. B is the data somehow related with the magnetic field, perturbation of magnetic field. And then chi is you try to susceptibility somehow related to the ion content. You try to reconstruct that deconvolution problem. Okay, data, but look at this one. This one is the kernel is the degree -3, very singular. So this kernel should understand as a principal value. Okay, so not diffusion thing. That's the convolution is somehow singular. So if you look at this structure, it's very much like the wave structure. Yeah, kernel is like a wave structure. So the problem is that using this data, you try to reconstruct this one. The problem is that there is a noise in there. Small noise corrupt everything. Okay, I show the next slide. Next slide is that this is the data. There is a little noise like this type of thing. This is like a small noise. One local noise makes the whole sound sticking out. Because if we take the Fourier transform, the kernel, the convolution part is looks like this. So this one is the 0 over this cone. So somehow you have to use the L'Hopital's rule at the k-space of Fourier space. But L'Hopital's rule is the image space. If you use the L'Hopital's rule, it's okay. But if you try to use the L'Hopital's rule and the Fourier transform, it's complicated. So there is a lot of problem. This is also another convolution problem, but it's not diffusion, but it's a singular, but it's because of noise is propagated. Noisy. Okay, here is the problem. Noise is just sitting there, then it's okay. The problem is the noise is propagating all over the place. That's the problem. So people developed he hired many mathematicians, and he is Cornell University. He's hired to deal with this type of so some mathematicians use the total variation then handle it. Okay. Yeah, actually there is a lot of paper about I'm going to minimize the total variation L1 and several things, something like that. Okay. But When he has a problem in funding, he first fired a mathematician for mathematics postdoc. He's not much successful in these cases. Yeah. And he is somehow used the compressed sensing or the total values technique. And this is my student result anyway. But it's you need to control the alpha and beta. So alpha and beta is the all the time I have to meet is why this image is then okay I change the alpha and I can change the beta. Then this is a troublemaker. Can you do it automatically? Yeah. Okay, I will do that. The postdoc do it, but it's never answer is for many years. So somehow total variation method is controlling in the regularization is somehow sometimes remove the important information. So that's the somehow challenging. So he developed the other method using the morphology of the MR data. He used combined network, deep network. But problem is that the QSM is a very important subject, but it's still robustness is not guaranteed. So that is not adopted in the hospital because sometimes okay, sometimes not okay. Okay. Now next, I also changed another topic. Oh, I have to give us another comment.
Just a question. In the MRI, can you see something if you have metal?
Metal?
If you have metal in an MRI, can you see something? Can you reconstruct?
This was not metal. This was
yeah, but is it possible? You don't know.
Somehow you know if you have a metal, somehow you know the metal subject. But it's here is there is no data you cannot reconstruct. Okay?
Yes.
But even though here is the image. Okay, here is the metal is this region, the metal is there. This is some image of CT image. Then something is there because if you take the X-ray CT. Okay, let's go back to the
MRI. Not MRI.
MRI is different. The MRI is the metal is you cannot the ion content. The blood contains is the ion content. So MR is somehow if you have the main magnetic field. Okay, MR is the main magnetic field. Because of the metal, somehow there is a perturbation of magnetic field.
Yes.
Because of the blood and something contains there is ion content.
Yes.
So there is usually MR machine try to make a homogeneous magnetic field,
Yes.
but because of the metal,
It is
it's
not
some perturbation. So in the long time, they try to remove that inhomogeneity. But recently, this is a useful information of the human body. So because of the ion content, there is something perturbation is there. Perturbed signal is the psi. Perturbed signal is this is the perturbed magnetic field. Okay, small, so very small. That's why it's very noisy.
Yes.
Very noisy. It's a small perturbation magnetic field. There's a big magnetic field, very small magnetic field is there.
Yeah.
Using that one, try to reconstruct the susceptibility. So its data is very noisy. Then that's the problem.
And if they are not noisy?
It's impossible. Not noisy. In order to reduce the noise, there is two methods. In order to communicate to each other, you speak loudly. That's the one way. But there is some limitation of the amount of the magnetic field. The other way is you repeat over and over again, averaging. But repeating over and over again is the patient standing in the MR machine. Usually, if you take the one MRI, that is 30 minutes. Then repeat over and over again, then take 1 day. Then who is doing that? There is a two limitation. The noise is inevitable.
So you are saying this problem is still open?
Somehow solved, but it's not robust. Sometimes working, sometimes not working. But sometimes not working, the medical doctor do not accept it. You can get the fund, but NIH fund, but it's a medical doctor will not accept it. So it's actually so far they use the prior information. The prior information is that there is a problem. He somehow removed the noise, somehow he evaluated the image, removed the artifact using the prior information. But here is the last one. Although the use of the prior information for regularization significantly reduced the streaking artifact. It restricted the range of possible solution, resulting in filtering out the clinically useful anomalous structure, because it's regularization is just to get rid of the anomalous structure. So how can we maintain the anomalous structure with the regularization? That's the key word in medical. This is the last example. This is my main field. Here's the example 3 is the electrical tissue property imaging. I think many people, many mathematicians studied this EIT system, and recently MREIT electric potential tomography successful. MREIT is I'm the founder, and this part is based on the Siam review in 2011. Okay, this is also same. Okay, here the electric tissue property imaging is that the mission is that these problems are ill-posed, but you try to find the ill-posed. Whatever you're working hard, but ill-posed. You have to find the well-posed part. Having a ill-posed, you have a trouble. Yes. So mission is to develop the well-posed system to solve this thing, certain percentage. Here, U is the conductivity or permittivity. B is the measured data. Measured data is somehow boundary current voltage, or that is called Dirichlet-Neumann map. Or using the MRI scanner, then there's magnetic field. Here, A is the sensitivity matrix. Sensitivity matrix is usually called the Jacobian matrix. That is made from Maxwell equation and data collection system and domain geometry. But interesting thing is the sensitivity matrix is mainly depending on the domain geometry and the data collection method instead of the Maxwell equation. The most important part is the boundary geometry and data collection system. The reader progress on the people spend a lot of time last 40 years for this subject. The main reason why this is not successful is that people too much focus on this Maxwell equation instead of looking at the data collection and boundary geometry. Okay, here, okay, that's why my lesson is that many people avoid over engineering. I don't know what the meaning of the over engineering can be modeling. Too much deep into mathematics, and too much is deep into the cell structure and the hard-kill Huxley model, then you fail, then you get the result. Anyway, this is the two method is that if you inject the current using the attached electrode, then current is flowing here, then the flow of the current depending on conductivity, permittivity. This is current density, this is magnetic field. Also, the other way is that you use the eddy current, so the sinusoidal current, you induce the distance. So using the Ohm's law, you try to reconstruct the conductivity and permittivity. But there is because this one is ranging between the 0 Hz to the 100 megahertz, less than the 1 gigahertz. So this one is elliptic PD, either elliptic PD with complex coefficient, not the Helmholtz, but there is something reflection is there. More than 1 gigahertz, you can go up to the Helmholtz equation. Below the Helmholtz equation. Okay, what is the interesting? So instead of directly studying, let's look at the what is low. Okay, this is the main reason why you study the electrical tissue properties, you try to see the disease process. This is orange and this is two different orange. They have two different conductivity. Here, this orange and this orange is same. This is just a grind making a juice. This one is completely different because of the cell structure. The same cell line, same structure, but if we grinding this one, that is completely different. That's why we study the electrical tissue. Key word is that you have to look at the disease process. Okay, so here is everything is complicated. I quickly go over that. So below the 1 megahertz, that's called EIT. Less than 1 kilohertz MREIT, and MIT is around that MREIT. But these two things are a lot of trouble so far. In making a static imaging because of the fundamental limitation. Many people in the United States, also in Korea, including me, a lot of people studied many papers, more than 1,000 papers, so it's not successful so far, including me. Okay, so that's the reason why 15 years ago, I tried to develop this new model. I tried to quickly explain my story about this one. That's at the time I was age 40. It's around 40, around 16 years ago. And then some people suggest the MR method. So at that time I was a pure mathematician. So, but I have to study all of these things. How actually you try to find this sigma. This sigma is somehow related with this is MR signal, and this is MR image, and then this is K-space data. I need to know the whole thing. Also, this is somehow sequence, pulse sequence. So it's I realized at the time I need to know everything. So nobody helped me, our group. Some people suggesting that's useless, just to giving that I have to do everything. So suggestion is that I found this less useful. So using that one, you try to, I will not detail of this thing somehow. Okay, this is, someone talk about the phase graph busy. Also at the time, you also unwrapping algorithm, also silent. Without looking at the unwrapping algorithm, you just develop unwrapping algorithm. Okay, here is this thing. Okay, before that, this is a data, and this is a conductivity, and this is U is the electric potential. And then 1992, someone tried to reconstruct the least square method. Okay, here is the data. Here is the you want to recover the sigma. U is the non-linear function of sigma. And then doing the some iteration algorithm, but somehow it's many people in the engineering just doing the data least square algorithm without looking at the structure of the data. So they spend a lot of time and then get this poor image because it's this data is a sigma and this relation is too sensitive. It's not sensitive. Small, this one contains a small, this data is a small tape, very tape contains this information. How can I reconstruct? So using this least square method is not successful. So people forget about this method because it does not work at all. But 2001, you look at this one, and then you develop something this direct method, and then you get a very nice image. So at the time, you are very proud of this thing. The problem is that when I say engineering conference, you are very proud of that one. But more criticism than congratulations at the time. Whenever I found something, the more criticism than congratulations. The main reason is that how can you get the full magnetic field data? MR, at the time I do not know the MR, at the time I'm pure mathematician, so I just answered that one. But but it's because MR just measure the BZ data. You don't know the BXVI. Then how can you rotate human body MR machine 90 degree and that one? Then you can get the 3-component data. And it's the other engineers are laughing. How can you human body rotate it? Even for babies, not so easy. So it's measuring this component requires the impractical subject rotation. So this is you realize this is impractical. So many people said that only BZ data, it may be you will not successful in providing the conductivity image. So it's, everybody criticized me, and okay, you are correct. But later on, I found that if we take the Laplacian, and then I found the one directional derivative of the log of the conductivities you can measure. Aha, and you can get it. And then you apply the two current, and then you are very successful in the reconstruction algorithm. This is our first image of the conductivity. And this is a very high, you can get a very high resolution. And then you start to the animal experiment. But animal experiment is a phantom cases. Okay, here is the phantom cases. Domain is the given. Neumann data is given around here. That's easy. But now you move to the animal experiment. At the time, Korea has nobody do the animal experiment at the time. That's the 2004. You are somehow the beginner of this animal experiment. But at the time, the domain, nobody give me a domain. Nobody give me a Neumann data. We have to find the domain omega. Usually, whenever you study mathematical, let omega be given. Okay, but that is not given at all. I have to find the domain. Neumann, and the Neumann data is given something like the L2 boundary omega is given. That is not given. I have to find what is the Neumann. So at the time, I start to study the image processing using the level set method at the time. So I studied that one. And then you develop the MATLAB toolkit, and here is all of these things. The MATLAB toolkit is use the level set method, the segmentation, and then you try to find this one. So we are very successful, and then after that you are very successful in the animal experiment. So far MREIT is the most advanced conductivity imaging technology now, and offer the state-of-the-art conductivity imaging in animal and human. Here is human. Until now, static imaging, not successful in the animal experiment so far. So here is the MR imaging, but the conductivity is different thing. Now you try to commercialize that. Then because of this, I got several prizes in Korea. A problem is that can I commercialize this one? The FDA safety mean limit is the 1 milliampere. Oh, but okay. Animal experiment is that's the animal, so you have to give the enough current and then to get the good image. But human body case, I cannot apply the enough current. So the safety limit is 4 milliampere, but our experiment say 5 milliampere is needed to get the previous images. But there is somehow you have to cut out this 80% of the. So why is reducing the amount of the current is low as signal to noise data, and then this produces the reconstruction and artifact. You need to handle the noise. But it's so far you are just stop that one because it's handling this noise is too difficult. So it's when you study this thing, you have a lot of lesson. You thought you are successful, then something, there is another hurdle after another hurdle. So you are waiting for the new development of the technology. Okay. Okay. Now quickly explain the EIT. This is the, I think most people know that this is my last topic of EIT. EIT area is that look at that. You apply the current here. You measure the voltage here. Using the boundary current and voltage data, you try to reconstruct the conductivity image in the EIT. That's the EIT problem. But look at that. Okay, here look at that. If you inject the current, if you apply the Neumann data, then this is a solution of the elliptic PDE. But structure of the elliptic PDE is not much depending on this thing, mainly depending on the electrode position and the geometry of this thing. That's the main thing. This one is maybe some tail part of it. But the last 30 years, more than 35 years of research is mainly focused on this part. Omega is given, Neumann data is given, and they're doing that one. That's why it is not applicable in the realistic situation. Okay, here is let's start this is Wisconsin professor, Mr. Webster, designed the impedance camera. At the time, it's 1970s, CT MRI is developed. So he thinks if you apply some project X-ray data and you can get data, using that data, you try to reconstruct. Same thing happened in EIT. But EIT is you cannot control the pathway of the current. MRI, CT is you can control the pathway of the energy. But the EIT is somehow depending, everything is depending on the conductivity distribution. But why many people study this EIT system? Calderon is my grandfather, because he's the harmonic analysis, his grandfather. He is somehow give the motivation of the study of the inverse problem. So mathematical inverse problem to identify the conductivity using this is called the Calderon problem. So that's the reason why many mathematicians all over the world study that one. But so if you have the full Dirichlet-Neumann, all full Dirichlet-Neumann map is the Neumann to Dirichlet data, you can could reconstruct. And then that published a lot of analysis papers and a lot of papers there. And so that's why they trust too much about the Calderon and many people. I also write a paper about that one. They try to take the many electrodes as many as possible to get the approximate of the Dirichlet to Neumann map. In order to use the Nobel mathematical theory developed by the very famous mathematician. And then this is I showed that there's some England group is I just copied it. And they make attach many electrodes and then try to reconstruct sigma. This one's a terrible misunderstanding. Terrible misunderstanding is okay, here is the domain. Here is the electrode is here. Electrode, okay, let's do electrode. Okay, in order to use the Calderon problem, let us attach many electrodes here. Why you attach the electrode? Let me suppose you apply the current here. Current is here. The current is going because Neumann data applied here. The current is electric potential. Solution is somehow satisfied something. So solution is satisfied. Sigma U is equal to 0 in omega, and the normal derivative of is equal to G. Is like this one. Most of people think about it. That's not true. That's not true. It's not here. Okay, here is look at here. Electrode is sigma is infinity. Sigma is 0 and finite here. Because you cannot handle the sigma conductivity infinity, you can feed away, and then you replace that one. But electrode distance is like this, then this equation is correct. However, electrode is very close each other like this one. Most of current is flowing in that direction. Okay, it's the same as you talk about Laplace multiplying operator. Conductivity is the small, meaning is something like a mountain. Conductivity is infinity. That's the kind of speed length. Okay, here if you apply the Neumann data here, they try to find the shortest distance between them. But what is the shortest distance? Just the current flowing there. So there's no current inside. So this one is the terrible misunderstanding of that. That means that he just studied the textbook. Textbook do not tell about this type of things. So just study the textbook, that is a terrible mistake. So no current is inside here. How can you reconstruct? So it's, this terrible misunderstanding happens all the time. Whenever I participate in the conference, some people say talk about this. So it's this type of lesson is somehow when you do the mathematical theory, somehow you need to do the real practice. Then somehow you can get it. So okay, I quickly wrap up it. So in order to understand the geometry, then I studied what is going on. In the cylindrical, this is the cylindrical domain, you apply the current, then conductivity is something like surface area length, you can get it. But domain is actually, this is not simple. This is even for the 4 electrodes like this, the finding of conductivity is mainly depending on the geometry and this one, okay? So, in order for our theory to be applicable, you need to understand all of this. I quickly finish this one. Okay, I studied this one, something like, I studied some, because my major area is layer potential and polarization tensor, somehow I used some that one. But the interesting things I would like to tell one thing. I studied single layer potential and double layer potential, and I was a student. But I didn't know why people say single layer potential, why people say double layer potential. So I asked many people, why is the single layer potential, why does it? Nobody answered. But it's later I found that is related with the cell structure. It somehow is frequent. In the frequency paper, I realized that. Anyway, when I studied this thing, I start to understand what is the origin of the something. And then you did this thing, and then this was commercially very successful. This is a great idea. If you go to the sports center and the health exam, you can check your 4 electrode here and 4 electrode hold that one. You check the body content. I think most of people have that experience. The idea is remarkable. You apply the because it's everything is depending on the geometry. How can I handle it? Because position of electrode is also touching a position of electrode, then depending on something. But you apply the current this direction, and then current apply this direction, current apply this direction, current depend on apply this direction, and then using this one, you cut off this thing just to look at the body. That's the key idea, and he became a millionaire. It's was somehow very simple idea, make him billionaire. But this is just a formula. But mathematician is too much over engineering, over science. So it's I try to emphasize, don't do over science. It's a simple engineering is best. Okay, so I quickly recently we also do the impedance geometry. Yesterday you talked about the finding equality geometry. I spent a lot of time, I gave up. But recently someone developed a 3D scanner. And then this is my body. At the time I did not do my body. And then using 3D scanner, you can catch up the boundary geometry error and the electron position error as much as possible. And then you could reconstruct. And then you do this one. Actually, this is a movie, but I cannot see it. And then also, actually, you evaluate the data, then you also this is movie I quickly wrap up this. And then after that I wrote the 2 books for the nonlinear inverse problem in imaging, and then also is electromagnetic tissue property, MRI as well. Because I learned many things for this thing, so that's the reason why. So lesson from 3 decades of this is my electroimpedance imaging. The symbiotic interplay among the theoretical mathematics, computational mathematics, and experiment is crucial for understanding and solving its nonlinear problem in practice. Understand how to probe the imaging object, what are measurable, this part is difficult, what are measurable using available engineering. That's it.
Thank you for the interesting lecture. Question, curiosity? Okay.
You mentioned some sort of negative experiences with TV implanting for this kind of things.
Oh, no, I use the TV implanting lab, but I just explained the negative part.
I actually would confirm your negative experiences. We use implanting methods for image compression, and we tested a lot of operators. And actually, the worst implanting you can do was TV implanting. All the methods. It's a goodly noisy operator, but for implanting, it typically gives you too much simplified representation of the statistics of natural images. Something like piecewise constant is simply not very realistic, and often it even ignores the data. It just tries to find a median in between, and that is not what one typically wants.
Yeah, that's I'm just the inside of the medical imaging area. Medical imaging area, but outside of medical imaging area, then you can use the total range of whatever you want. But medical imaging is a little bit different.
Other question?
May I have one comment on my earlier question with the sinogram? When you, for instance, take the total variation of the radon transform of an image, then it will actually produce not like just like Joachim was saying, like it's usually is the problem with TV, that it will actually then just make homogeneous areas in between. It will then actually produce something different that is actually by producing a sinogram that's in the range of the operator. So it will not just fill it up with, which then is obviously also a different operator. It's a gradient of the radon transform. And I think, because it looked initially as if you sort of compared it like with a normal TV implanting, but I mean, when you do the TV on the radon transform, it gives you completely different results, and that may already work quite well for the implanting problem, to my experience. It makes quite a difference.
I checked that spread it across the entire image. I mean, you've now taken the effect of your over smoothing, and you now, you apply the inverse transform, it applies to the entire medical image now. So you've induced a difference from the real that's now systemic versus localized.
Well, now, what do you mean with localized in that sense? I mean, you have missing information, and you somehow have to fill it up.
Yep, and your choice you've made in filling it now affects the entire image.
No, I mean, it doesn't have to be. I mean, I can just take the strip that I want to exclude, say outside of the strip, the sinogram stays the same, but I fill it up in the sense that my sinogram is actually a proper sinogram, and not like, I mean, it does not necessarily then need to affect the remaining part of the sinogram.
No, I'm not talking about the image that the clinician looks at.
The image the clinician,
they're making a diagnosis.
That's
the image they're looking at, while looking very correct, is not real in a systemic way because you've modified the sonogram. And this is the thing that there's resistance.
Yeah, you're right. This is true. Yeah, but this is true.
I would like to explain the one thing is someone told me the Gauss curvature driven and some image processing. If you look at all of these things, everything is Gauss curvature 0. So I thought Gauss curvature driven regularization is the best. But I do the real thing. But Gauss curvature driven some regularization is too much strong. They connect the all noise and make the new images. So it's somehow sometimes it looks good, sometimes it exactly fits the reality, but sometimes there is a side effect. The medical imaging area is Okay, in order to step tomorrow whether tomorrow is raining or not raining, you have to all the time, wrong is all the time wrong, right is all the time right is correct. But sometimes correct, sometimes wrong. That is the really difficult. It's difficult to judge. So difficult thing is that somehow how can I get the robust thing? It's repeatable and reproducible. That is the then you can get the data. You can. But it still is a TV painting. So somehow you need some modification.
No, what I would just like to emphasize is that many people are using TV-like techniques in an uncritical, rather religious way, and are not questioning whether a certain operator is really good or realistic as a model for the real world. For human-made objects, something like piecewise constant is what you can see all around if you look here. But if you look at the real natural images or medical images, things are different.
Yeah, that's a good point. Yeah.
Last question, Kitchen. Except in the case if you
I'd
have
like to
metal.
I'd like to ask a quick, simple question. You haven't talked a lot about numerical algorithms. What sorts of algorithms do you recommend for your?
By the way, I'm not expert of the numerical algorithm.
You plotted some.
Yeah. Usually I'm making somehow theory and modeling. So I do not have enough ability to answer numerical. That's my weakest point.
Okay, we can thanks again. Now we have break till 10:50.
This morning break is really fun.
So I'm actually at the medical school.
Okay.
It failed.
You're absolutely right, because I would most likely not do. I would always try to do something in the image domain to acquire information. Or well, I'd say I would try to acquire the information that I'm interested in the first place, and not like some sort of.
Vado a capisci quante cosa mi dice Enzo,
Yeah, may not be clinically. That's true.